Right.
Let me show you where it's all located. We go to Files, just related. Here's the practice test I'm going to go over on Monday. Here's the study guide, and here's the take-home problem. Now, excuse me. The take-home problem is due on Tuesday, and you're just going to bring that in and staple it to the back of your test. So on the practice test, this is very similar now to your real test. I make special pains to make sure that what I tell you to study is on the tests. Now, there's two major topics we haven't covered yet. Well, actually, three counting tonight. Tonight, we're going over Lewis dot structures, which is going to be your dry lab for Wednesday, Thursday. And then single and double replacement reactions, we're going to go over Wednesday, Thursday in lecture. So, all right. So everyone clear on where everything's located? Drink water. Okay. All right. Let's go ahead and look at Lewis dot structures. Oh, one other thing. If you go to Files, Lab Related, the two dry labs this week I've modified, much to your liking, hopefully. This guy and this guy. So please download those. You'll find those, in my opinion, much more straightforward than the ones in your lab packet. So
That was 5 and 7, right?
I'm sorry?
That was dry lab 5 and 7. I
Yeah,
think I've already printed them, so I just want to make sure. Okay, 5 and 7. I'll reprint.
but which one did you print? The ones
I
that,
think I printed well, you uploaded them yesterday. I went and printed them all yesterday. You know what? Maybe I printed them right after you uploaded them.
I tell you what, let me go back and show you what those look like to make sure you, okay, so this is 5.
Five.
So this is basically, you've got the formula, name it, you've got the name, give me the formula. Can you
Okay.
be, is that the one you downloaded?
I downloaded quite a bit of stuff.
This doesn't have like 5 pages of instruction.
Okay.
Professor,
Yeah,
just to clarify, for lab 5 and 7, you only want us to do part 1 on both pages, right?
yeah, and on this lab 5, don't do the ones that say AQ because those are acids, and the ones that say acids, like
So is
oxalic acid, hydroselenic acid. Don't do those because we haven't covered those. Do the ones that don't say acid and don't do the ones that say AQ.
okay. I think I might have printed the other one because the other one is also labeled the nomenclature workshop also. And is it 1, 2, 3, 4?
Yes, yeah,
There's 5 pages.
I purposely named this one the same so you wouldn't get confused. But the main deal is this one's significantly more straightforward. That's the bottom line. Because if
Okay.
you look at the directions on how to do these, they're very complicated in my opinion, unduly so. Just
Okay.
These will follow what we went over yesterday in my lecture. Okay.
So I've already printed the other one and I'm like on page 4. So I've been working on it today to understand the concepts. Is it necessary for me to print this one also? I don't mind. That's fine. But I've already started working on the first one that you uploaded because I printed them right away.
You can turn in either one.
Okay.
I think this one will be of more value.
Okay, I'll take a look at that one as well. Thank you.
So we
Okay.
wouldn't have to complete the whole lab 5 and lab 7, just the part 1s.
Well, there's no part 1 in lab 5. It's just
Well,
this
there's
is-
a section that says part 1 and then it leads to part 2. So I just want clarity on like would we need to complete the whole packet, or is it just the part 1?
yes. On lab 5, do the whole thing.
Okay, so we would complete the part 1, part 2 up until page 6. I meant
Yeah.
part 6.
Yeah, they don't call it that, but yes. They
Okay,
call it A,
sorry.
B, C, D, F, basically you're just been formula to name to formula. And you need lots of practice doing this. And here's an AQ, so you wouldn't do that one. Here's an acid, so you wouldn't do that one. We'll cover the acids when we get to the acids and base unit, subunit.
Professor, can you repeat which ones you said not to do? You said AQ and which one else?
Acid, like for
Acid.
example, this one here, carbonic acid.
Okay, thank you.
And then the dry lab molecule. You should have seen me this morning. Okay, these are directions that I have horrendously simplified compared to the directions you have in your dry lab. And this is what we're going to go over today. Okay, and then Wednesday, Thursday, we're going to be doing we're doing the name. Wait a minute, we're doing the nomenclature. Let's see. Yeah, we're doing Lewis structures for Lab 7. This guy here. And you've never heard of Lewis structures. Probably this is what they look like. Now I've given you the answers also. So everyone should get an 11 unless they don't want an 11. But I want to make sure you're on the right track. Because if you do them wrong, then you've got to unlearn what you've done and relearn it. And so I give you the answers. Okay. And there's a whole bunch to Lab 7 that I don't think is in the scope of this class. The Lewis structures are real important. And I want you to leave this class with Lewis structures in mind. So that's what we're going to talk about tonight. Okay, so we all okay on where to find this stuff? Okay, so.
I think someone's mic is on. You can hear the background.
I think it's Shantik. I sent you.
Okay. Lewis dot structures. Now the dots refer to something called valence electrons. So what are valence electrons? Okay, if we look at lithium, on the periodic table here, it has 3 electrons total. So if we look at Bohr's model, we've got the nucleus and we've got these orbitals, solar like our solar system. Okay, the first orbital can only hold 2 electrons. Next one can hold 8, etc. Now, since lithium only has 3 electrons, the 2 electrons are going to occupy the first one, because that's the most stable orbital. Then the one left over is going to be on the next one out. So valence electrons are electrons that are in the outermost orbit. So in lithium's case, it has, so there's 2 electrons here. Let's do this bigger. So that's 3 electrons for lithium. So the outermost electrons is this one here, and that has 1 electron in it. So lithium has 1 electron. Now, if you remember from our periodic table discussion a while back, everything in this group has 1 valence electron. And the next group over has 2 electrons in terms of valence electrons. 3, 4, 5. 6, 7, 8. All the groups. So oxygen, all of the elements in the oxygen group have 6 valence electrons. Nitrogen group, all of them have 5, carbon's got 4, boron's got 3, etc. Now that's all the electrons we're going to be dealing with. It doesn't matter if, for example, excuse me. For example, selenium here, it's got 34 total electrons. But it only has 6 valence. Okay, so there's a problem. It's when I talk, I cough. I make my living talking. So this is okay, so total number of electrons. Let's look at lithium again. 3 electrons total. Of those, the outermost electron has got 1. That's called valence. And the other 2 are called core. Totaling doing well tonight, huh? Totaling 3. So there's only 2 kinds of electrons, core and valence. Valence are the ones where all the chemistry takes place. Core are core are extremely stable. So the valence are unstable. And the core are very stable. So this is where the chemistry happens with the unstable valence electrons. Now, the reason why the chemistry happens is because the unstable valence electrons want to become more stable. So if we look at these guys, these represent the valence electrons. Now, you need to know these. Five of those. Let's look at sulfur. Where's sulfur located? Sulfur is located underneath oxygen. So whatever oxygen is, sulfur is the same thing. So if oxygen has 6 valence electrons, so does sulfur, so does selenium, so does beryllium. Oops. Didn't want to do that. See here. So these are at the top of the columns. So carbon's got 4, hydrogen has 1, oxygen has 6. However, what's important about oxygen is it has different setup. Same with nitrogen. Notice that nitrogen and oxygen have singletons. And, oops. Doubletons. Now, it's important to distinguish between the two because the only things that are going to do bonding are singletons. Okay. Now, I mentioned on I think it was yesterday, there are 2 kinds of bonds, covalent, molecular. This is rainbow colors. We don't want that. And ionic. Now, when we do Lewis structures, we can represent both of them, but I'm going to focus on covalent for this lab. Ionic means we have to deal with either one less electron or one more electron. Now, covalent means co, meaning share. Valent means valence. So a covalent bond shares valence electrons. And that's where most of the Lewis structures kind of operate in. We're going to be sharing electrons, and these are singletons. Electrons as well, not the doubles, not the pairs, only singletons. So if we look at carbon has how many singletons?
4.
4.
It means carbon can do 4 covalent bonds. Hydrogen,
1.
1 covalent bond, etc. the paired up electrons are already fulfilling their requirements for stability. So when two singletons pair up, they're horrendously more stable than by themselves. So that's why with oxygen here, we've got singleton, that means two bonds. Two pairs. Now they're already paired up, so they can't have more than two in an orbital. That's why the singletons can occupy another atom's orbital and share that. Just like if two people rent an apartment, you share everything, occupy the same space. It's exactly the same thing. Okay. And to reiterate, notice sulfur here looks just like oxygen because it's underneath. Phosphorus looks just like nitrogen because it's underneath. So notice chlorine and fluorine. It has three pairs and one singleton. That means you can only bond once, one bond. Boron, it's got three singletons. Now, you might ask yourself about carbon. Why doesn't carbon have any pairs? Carbon is special. Carbon is special. It undergoes something called, and don't write this down, bond hybridization. And it takes the paired electrons it started with and separates them into four singletons. And that's out of the scope of this class. So in your next class, you're going to be 306 in the next class. We don't go over that in there. Well, anyway, carbon's the exception, and everything underneath carbon would be the exception as well. Okay, so 4 bonds, 1 bond, 2 bonds, 3 bonds, 2 bonds, 3 bonds. You see where I'm getting these numbers from? 1, 1, 3. Because I'm counting the number of singletons each time. Now, Dr. Lewis, back 150-ish years ago, they would get things like this. H2O. And they wouldn't know what it looked like. So what Lewis tried to do was to put some kind of spatial cognition around the formula. And that's what Lewis dot structures are all about, is to give it some kind of a three-dimensional, mostly two-dimensional, but shape to the formula. And then that can then be, you can predict physical characteristics of that molecule based on its shape. Okay, so let's do some of these problems here. All right, let's look at hydrogen gas, dihydrogen. It means there are 2 hydrogens. And each one has got a singleton. Now, a singleton by itself is very, very, very unstable. It's called a free radical. And they bond to anything. Atomic bombs produce a lot of free radicals. That's why they're so dangerous. One of the many reasons they're dangerous, but this is one of the reasons they're dangerous. So to make these 2 molecules happier in a more stable place, they share an orbital. 2 electrons per orbital. Each one has 1, so 1 plus 1 is 2. So they can share that orbital. Now, Happy times pervade. The next thing you do is replace the shared bonds, the shared orbitals with a single line. So that's the Lewis structure for dihydrogen. Now I've got a list of steps to go through, and this is part of the steps. Okay, so let's do another one. Dichlorine. Chlorine has got 7 valence electrons. Only one singleton, though. Those singletons now, just like hydrogen, can share an apartment, share an orbital. Now they're much more stable. We can replace the circle 2 singletons with a solid line. So this is Lewis structure for chlorine gas. So are there any questions so far?
So for the dots that go around the symbol or whatever, it doesn't matter what order you put the pairs or the singletons or whatever.
Excellent question. Her question had to do with where we put the pairs and singletons, right?
Yes.
Okay, yeah, it doesn't matter. For your convenience, we can put them anywhere you want. So if we did it like this, tell me which one you like better now. So for your convenience, just move them around so that things align better. So did that answer your question?
Yes.
Was that it? Was that a yes?
Yes. Sorry.
When you said you have steps for this, what were you referring to? When you said there's a moment ago, you said like I have steps for this process, or maybe I misheard you.
No, you didn't.
Okay.
There are, I didn't load it. I need to load it here real quick. First, I gotta find it now. Okay. All right. So let me do a couple more before we go into these steps. But this is the steps I was talking about. Okay, so let's do this one. So that was NI3. Step one is choose the most complicated one in terms of numbers of singletons first. Okay, so if we go up to the top here, and we look at nitrogen, it has one pair, 3 singletons. Iodide, which is underneath fluorine, has 1 singleton. Okay, on the periodic table, here's iodine, and it's under fluorine. So that means that's 1 singleton. Okay, so which has the most singletons, nitrogen or iodine?
The nitrogen.
Huh? Which has the most singletons, iodide or nitrogen?
Nitrogen. Didn't you say it had 3?
Yes, exactly.
Okay.
So that's going to be in the middle. And this is what iodine looks like. And we've got 3 of them. Okay, so that's step one, putting the atom with the most singletons in the middle. Step 2 is connect everything up with 1 bond. That means 1 singleton to 1 singleton. Okay, so we've got 1 here, 1 here, and 1 here. Now notice I put the singleton kind of closest to this other one. I could have put it over here, but it'd be kind of a goofy attachment. Okay. Step 3 is, are there any leftover singletons? No. Now we go on to step 4, and we have to determine whether this is a legal molecule. Okay, these are the legal steps. There are 2 parts to this. Let's do the first one first, or the second one first. Okay, so carbon needs to have 4 bonds, nitrogen has 3 plus an electron pair, oxygen needs 2 bonds. Now this is after the connection's made. 2 bonds plus 2 electron pairs, hydrogen's 1, halogens are 1. Okay, so let's see how our nitrogen did. Okay, nitrogen needs 3 bonds. Bond, bond, bond. 1 electron pair. So nitrogen looks good. What about iodine? Iodine needs, because it has 1 singleton, 1 bond. 1 bond, 1 bond, 1 bond. So the number of bonds is good. Now the next step is to talk about a full shell. What I mean by that is 8 electrons. Sometimes they call this an octet. Now, the reason why I don't call it an octet, because hydrogen only has 2 electrons to have a full shell. So hydrogen has 2. Everything else has 8. So hydrogen's full shell has 2 electrons shared in it. Everything else has 8 electrons. And okay, so let's look at this. Now we're counting electrons, including shared electrons. So we have 2, 4, 6, 8 for nitrogen. 2, 4, 6, 8 for each iodine. So this is a legal structure. Now, the last step is to take all the bonds and put lines in it. So it would be like this. That's the Lewis structure. Following these steps. Now, if you were to ask someone in the 305 class, there's another way to do this, which is much more complicated. I developed this about 30 years ago because this takes care of 90% of the molecules that you run across. And it's so much easier. The other method, you have to total the total valence electrons, and then you have to fulfill a single bond, and then you have to do double and triple bonds to make, anyway, this is much easier. Okay, so did that make sense with nitrogen triiodide? I know you've heard. I know you've never seen it before, but were you able to follow the steps with me?
Yes. Will this be posted anywhere, Professor, or should I just come back and rewatch the video?
Well, I'm not done with the video yet.
No, I just meant the step process.
I mean, the other process or my process?
Your process that you pasted underneath here, is there going to be a sheet that this could be posted in, like on Canvas?
Yeah, well, this is on Canvas here. Is that what you meant?
Yes, it is. Sorry about the confusion. Thank you.
No, that's fine. That's fine. Please ask questions. I've had 2 hours of sleep last night with a little cat naps during the day, so I'm easily make mistakes. Okay, let's do some.
Professor.
Yeah.
Was there a rule on showing, I mean, how do you, when you view it, how do you know that it's legal or illegal, like you said?
Yeah, right here.
What?
4 and 5 have to be both met. One is the full shell, in other words, 8 electrons, except for hydrogen, and then the number of bonds for each element. So carbon needs 4 bonds, nitrogen's 3, oxygen's 2, hydrogen's 1, halogens are 1.
So
That-
basically these are like rules. So like any molecule
Yes.
created, carbon will always have 4 bonds. It's
Yep.
never going to be, okay, that's just how it works.
Yep, exactly. Because of the way the valence electrons are laid out. The valence electrons are in either singletons or pairs, and the only bonding can take place with a singleton. And there's one exception to that I'm not sure it's in the scope of this class, but anyway, there's one exception to that. But basically, these are the rules. Boom. 4, 3, 2, 1, 1. I'm going to get into more examples here. So you'll see how this flows. And then the last one is replace the bonding pair of electrons with a solid dash. Okay, so let's do a fancy one here. Let's do C2H4. This is ethylene gas. Ethylene gas is produced by bananas to ripen fruit. including itself. So this gas is what they inject. What they do, for example, with apples, they pick them all in the fall. Some are green, some are fully ripe. The green ones they put in a special place and they don't do anything. They deprive them of all kinds of gas. And then when they want to take them out of storage, they zap them with ethylene gas, and the ethylene gas ripens them. Or you could have thrown in a bunch of bananas. Normally they just use raw ethylene gas. So this is ethylene. Ethylene. Okay, so let's do the Lewis dot structure for this guy. Now we're talking about 6 atoms now, so we're starting to get up there in numbers. Okay, so between carbon and hydrogen, which has the most singleton electrons? Remember up here? Carbon or hydrogen?
Carbon.
Carbon, right. Okay, so those are going to go in the middle. Now, we're going to surround those 2 carbons with 4 hydrogens. Doesn't matter where. And I'm just going to kind of divvy them up since we have 2 carbons. Now I could have put the carbons both on the bottom, both on the top. I could have put 3 on one, 1 on the other. Okay, so that's step number 1. Okay, oops. Okay, so step number 2 is to connect everything with one shared orbit or bond. So that's 1. That's 1. That's 1. Okay, step number 3 is, are there any non-bonded singletons?
Yes, there's 2.
Exactly. So what we have here is a free radical, very, very unstable. So we need to connect those up so it's more stable. The problem is it's kind of awkward the way we connected up this part here between the 2 carbons. So instead of connecting up like that, let's connect it up slightly different so that it isn't so awkward. Let's do it like this. Now we can connect them up. So now there are no singletons left over unbonded. Are we okay so far?
Okay. Yes.
Okay, good shape. Now we need to check for legality. How many bonds does carbon have? Well, we have 1, 2, 3, 4. 1, 2, 3, 4 for the other one. So carbon's in good shape. Hydrogen, 1 bond, 1, 1, 1, 1. So now we look at shell. So there's 2, 4, 6, 8 electrons for carbon on the left. Carbon on the right's got 2, 4, 6, 8 as well. Hydrogen's got 2. So both those steps make it a legal structure. So now we're going to add lines for each bond. So that's what ethylene gas looks like. Now, if you take my 306 class, I have Dry Lab 0. And Dry Lab 0 reviews Lewis structures. because the whole semester you're drawing structures. Whole semester. So that's why it's crucial that you understand this. Okay,
Professor,
go ahead.
we can set it up any way we'd like, though. I can do both H's on top and both H's on the sides as
Yeah.
well.
Yep.
Okay.
Yep. Mhm. And also, remember, molecules move. There are 5 modalities of movement of molecules. There's translational from one spot to the other. There's rotational. There's wagging. There's all kinds of movements possible within a molecule. So this thing could be tumbling, and it could look like this. So that's exactly the same molecule. It just tumbled, which is kind of where you were going with your question about the hydrogens.
Professor?
Yeah.
I came into class a little late. Where can I find the Lewis structure instructions sheet thing? Like how to do the Lewis structure stuff?
Right. You're talking about this here?
Yeah.
Now, why don't I have a stop share? Yeah, I'm in files lab related. Um, oh, it's already there about that. Hmm. Well, you'll find it in here. Files lab related. And I'll make sure everything is here after we hang up here. Because I only see 107. There should be more than 107. Okay, anyway, that's where it'll be as soon as we hang up.
Okay, thank you.
You're welcome. Okay, so let's let's go on. Okay, so that was, by the way, this is called a double bond. This here. So this is called a double bond, single bond, and then also carbon can have a triple bond, and so can nitrogen. So as long as carbon adds up to 4, so we have, for this carbon on the left, we have 1 plus 1 plus 2 is 4. 1 plus 1 plus 2 is 4. If we had nitrogen, now let's see, that's not a good example. We looked at N2, nitrogen gas. This is what it looks like. So nitrogen can have a total of 3 bonds. So this is called a triple bond here. So carbon can have a triple bond, nitrogen can have a triple bond. Oxygen can only have a double bond. So let's look at a oxygen. Let's do carbon dioxide. Okay, which has the most singletons, carbon or oxygen?
Carbon.
Carbon. So that goes in the middle. Oxygen is going to either be on both left side or both right side or 1 and 1. I'm going to do 1 and 1. Now carbon has got 4 singletons. Oxygen has 2 singles and 2 pairs. So I'm going to put the pairs on the outside here and the 2 singletons in the middle here. Because we're not going to bond to the pairs. So we'll put those on the outside. Okay, step number 1. Step 2. We connect everything up with at least 1 single bond. Next question is, are there unbonded singletons? Well,
Yeah.
2 on the carbon and 1 on each oxygen. So let's connect those up. Okay. Now let's look at the legality of this structure. Carbon needs 4 bonds. 1, 2, 3, 4. Carbon got its 4. Oxygen needs 2. 1, 2. The pairs don't count because they're already paired up. The orbital cannot hold any more electrons than that. So it's a legal structure. So now we've got that. That's what carbon dioxide looks like. So oxygen's got its 2 structure or its 2 bonds. In this case, they're double bonds. Okay, are we okay with it? Let's try another one. Now I'm going to end up with 2 legal structures for this. I'm going to end up with ethanol and dimethyl ether. Okay, so in the middle goes which ones? Carbon, hydrogen, or oxygen?
Professor?
Yeah.
I have a question about the one that you were just working on. Wouldn't the valence electrons,
I'm sorry, say again?
wouldn't we consider the valence electrons for that equation?
We did.
Oh,
We did-
okay.
We did up here.
Is it not 16?
Okay, so let's count. You're talking about the shell electrons?
No, I guess I'm just speaking because I'm looking at lab 7 and it gives us the same like equation that you're doing right now. And I believe I got the valence electrons, it was 16. So I'm just trying to understand, did I do something wrong or are you just showing us a different?
Well, they're counting total valence electrons for all 3 atoms.
Oh, okay. Okay, that makes a lot more
So-
sense.
4 for here. And then what you're going to, well, anyway, there's a different approach. And that's what is in your official lab 7. Okay, but we're
Okay.
just looking at only the valence electrons, okay?
Got it. Thank you.
Now, if you want to do that approach, it works fine. It's just more complicated. This is just netting it out. And use these guys up here. So a single carbon has got 4 valence electrons. 2 carbons has got 8. Oxygen's got 8, 6. Nitrogen's 5. Sulfur is 6. Phosphorus is 5. Chlorine's got 7. Fluorine got 7. Boron 3. Then when you start adding those up, see, my method doesn't take into account the electron pairs. I just throw those in and leave them there because they can't do anything. They're already paired up. So they're not part of the process. So you're working with far fewer numbers here. Let's see, where did our... There it is. Okay. So this one, let's go and work this one out. And I'm going to show you that there's another structure that's just as legal as the first one. All right, so we're going to do carbons go in the middle. Hydrogens we're going to spread around. Now the oxygen, you can put it on the left or the right. Let's just put it on the right. My dog wants to go out. You'll just have to wait. He's really old. I have 3 dogs. This one wants to go out as he's pushing 17, so. Okay, step 1, we've done it. Step 2, we need to start connecting up with single bonds, everything. What didn't we do?
Oxygen.
Yeah, we didn't connect anything to the oxygen. So what we just did won't work. We have to connect everything up with one bond at least. So let's go ahead and erase some of these bonds. So we need to connect up the oxygen. And we need to connect up with that hydrogen. Okay, so everything's connected up now. So let's check for legality. Carbon needs 4 bonds, 1, 2, 3, 4, 1, 2, 3, 4. Oxygen needs 2, 1, 2. Hydrogen needs 1 around. Okay, so bond-wise, it's legal. Let's look at octets. Okay, 2, 4, 6, 8 for the carbon on the left. On the right, 2, 4, 6, 8. Oxygen's got 2, 4, 6, 8. So this is a legal structure. Next thing we do is connect the bonds with solid lines. Now, that's ethanol, also known as drinking alcohol. It's a 2-carbon primary alcohol. Okay, so let's redraw this a little bit. And you're not going to see, if you look this up online, it won't look like that. what happens, we're going to straighten the OH up. So it'll look like this. So this is typically the way you see ethanol on the bottom. But on a test, if you put this one here, it's perfectly fine because it's legal. Okay, we okay?
Professor.
Yeah.
How did you know to put that oxygen you connected with like between the carbon and the hydrogen? Like,
Well, the first time we did it, we
put it,
didn't have
like,
oxygen
between the
connected at all. So we had to
right?
get oxygen connected. So once we did this first connection over here, that left a hydrogen unconnected and one singleton on the oxygen unconnected. That's why we did this one. Better? Now the oxygen can be, instead of off to the right, it can be on the top, the bottom, left or right. Doesn't matter. Because remember, these molecules can tumble in air.
Um, could you explain how you did the checking for the octet octet or the like with the bonds, like you said
Yeah,
each one had like 8? Could you explain how you did that?
yeah. Each single bond has 2 electrons. Each double bond has 2 and 2 or 4 electrons. Each triple bond has 2, 2 and 2 or 6 electrons. So we have 2, 4, 6, 8 for carbon. For the right-hand carbon, we've got 2, 4, 6, 8. This carbon to oxygen. Oxygen needs 8 also, so we have 2, 4, 6, 8. Hydrogen needs 2. 2, 2, 2, 2, 2, 2. Is that better?
Okay, yeah. So like only oxygen has two, everything else has 8, and it should be
No,
like that for
no.
everything.
Oxygen has 8
Nope.
also. Everything has 8 except hydrogen. It's got 2.
Yeah,
But with
hydrogen
oxygen,
has 2, and
yeah,
then everything else has 8.
yes, exactly.
Okay.
Now, oxygen has 2 pairs and it has 2 bonds. Each bond has got 2 because we're sharing electrons now. So we've got 2 bonds here, 2 and 2, and then 2 pairs. So that's where the 8 comes in. Okay. Okay, so that's one structure for C2H6O. Let's see if we can come up with another legal structure. Okay, I always said in the center to start with, put the atoms with the most singleton electrons, which would be carbon in this case. What if what if we didn't do that? What if we put oxygen in the middle? Like this.
That's what I was thinking, Professor. I was like, why can't you just put it there? What
Yeah.
tells you to put it over there instead?
Well, I always say start with putting the carbons in the middle as your first go around. And then from
Okay.
there, you can start deviating. So with the hydrogen, it's going to look like this. And then we're going to have 6 hydrogens. Step 1. Step 2 is connect everything up with one bond. Okay, any singletons left over? Nope. Okay, let's check for legality. Carbon needs 4 bonds. 1, 2, 3, 4 on the left. 1, 2, 3, 4 on the right. Oxygen needs 2 bonds. 1, 2. Okay, let's look for shells or octets. Okay, carbon on the left, 2, 4, 6, 8. On the right, 2, 4, 6, 8. Oxygen in the middle, 2, 4, 6, 8. So that's legal. So what this looks like, now, this is a conundrum. We've got 2 legal structures. This is called an ether. And you don't have to write this down. And this is an alcohol. They're both legal. So now as a chemist, you need to figure out your formula, which is it? So what you do is you do tests. You do tests for alcohols, see if your compound acts like an alcohol, or does it act like an ether? You can also run it through a machine. In 306, we run it through an infrared spectrophotometer that determines this kind of structures. But there's mass spectrophotometers, there's a whole bunch of instruments you can also. So there's wet chemistry and instrumentation to determine which of the compounds you have. Okay, the main thing here is you can have more than one legal structure. Now, if I asked you on a test, draw me a structure, I gave you the formula C2H6O, either one of these would be fine. Unless I said draw 2 legal structures, then you have to have both of them. How are we doing, you guys? That's as far as I'm going to go with legal or with Lewis structures.
That's
Not-
that's what I was saying, Professor. I forgot what you said the rule was. I don't know if I'm drawing on the board. I don't know if you see me.
yeah.
Because on the test, I guess, just naturally, I guess I would want to put the oxygen in the middle, but obviously that's wrong if we wanted to make alcohol. And I don't want to get it wrong. Like if you told me to write the structure of alcohol, and I have this
But
oxygen,
but they're
like
both
how did you know?
they're both correct.
But what if you told me to draw the structure of C2H6O?
Oh, yeah.
And like, how would I know which of these two correct structure? Like, what is the rule that tells me to bind it between the carbon and the hydrogen, like that, versus like this in the middle?
But my point is, the instructions I gave you in the beginning, I said, put in the middle the atoms that have the most singletons, which is usually carbon. I said, but then you can also, change the rules a little bit. You don't have to put those in the middle. You can put other things in the middle. Frequently, it's oxygen. Now, in organic chemistry, we have lots of carbon, lots of oxygen, lots of hydrogens, and all kinds of wild shapes. So if I gave you this,
So is hydrogen always alone?
no, it's not alone here. It's kind of alone up here, but not in the second one. Now, if we did another one of these, I'm going to do one more. Okay, so we got C2O2 H4. Okay, so the first one I would do is putting the carbons in the middle. And we have two oxygens now. Where do you want to stick them? We can stick them on the one on the left, one on the right, both on the right, both on the left. Throw one in the middle.
I guess my instincts are to split the hydrogens between the carbons, so 2 on 2, and then oxygen
Excuse me.
1 on each side too.
Say again. What was
I
your,
guess my instincts are to put hydrogen 2 on the left, 2 on the right for each carbon, and
Okay.
then split oxygen like maybe 1 on each side as well, just naturally.
uh-huh. Yeah, well, let's do that. Okay. So you said like this, two, right?
Yeah.
And the oxygens were on the bottom.
Yeah, it's like I wouldn't know where to. I mean, hydrogen only has one bond, so I guess it has to connect to the carbon.
Okay.
Does that break any rules?
And then we have one more. No. Okay. Does that look about what you're thinking about?
Yeah, I guess I have to go through the rules.
Now, this happens to have 6 legal structures, by the way. So
Can you help us understand where the 6 are when you say 6 legal structures? What are you referring to?
this had 2. In steps 4 and 5, you got to make sure the number of bonds and the number of octets were maintained. So this thing we can arrange all different kinds of ways and still maintain those 2 legality rules. So let's just do this now here. Do that, 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 that. And what are we going to do now? Oxygen is totally disconnected. Both of them. How can we fix that?
Wait, doesn't that oxygen can't combine to carbon? I thought oxygen has 6,
Well, it's
and it
got,
leaves one singleton on it. No,
but it's got 2 singletons.
1, 2,
2
3,
pairs and 2
4.
singletons.
It's got 1, 2.
Can't we connect the oxygens?
Yeah. So we can't connect them the way everything is sitting now, right? So
Would you erase the connections to the hydrogen and connect them there? Or
yeah, exactly. So let's connect those, this guy and that guy.
okay.
And let's go like this. Now, oxygen's the way I put them, it's kind of awkward because the singletons are down here in the bottom. Let's move it up to here instead. So all we're doing,
Doesn't carbon have 4 singletons?
yes, it does. Okay, so here's the 2 singletons for oxygen. So let's connect up the hydrogen to the oxygen and the carbon to the oxygen here. Same here. Carbon to oxygen, hydrogen to oxygen. Oops, maybe do this one here.
So can we rearrange the singletons anywhere around the oxygen? Is
Yep.
that what you just did? Okay.
So it's a little
Professor?
awkward looking now, so you can just kind of spread them out a little bit. So what you're looking at here, you're perfectly on the right track. So you've got, and this is a legal structure. Okay, we've got carbon's got 2, 4, 6, 8, carbon's got 2, 4, 6, 8. They're a mirror copy of one another. The oxygen's got 2, 4, 6, 8, same thing. Okay, so let's see what this looks like. Like that. And then of course we got to put the pairs in here.
Professor,
Yeah.
is there a reason we can't have like where you have like the H's connected to the carbons and stuff, and then if you connected like the oxygen to a carbon and the other oxygen to a carbon, could you not connect the oxygens together? Is that not allowed?
Oh, it's fine.
Oh, okay.
So you're talking about
Yes, Professor, because that's what I just did. I put the two oxygen in the
Okay.
center.
Oh, okay. This is what I thought you were talking about, which is legal, by the way. That's called a cyclic peroxide.
Yeah.
And then we can also put them in the middle.
Okay, so then which one do we? How do we know which one's correct? I keep
They're all
asking. They're all represented by molecules. So
Mhm.
if you told us
Step
to
4
draw
and
the
5.
Lewis structure for that formula, these are all correct.
Yep.
Oh, okay.
As long as step 4 and 5 are met. Octet and the number of bonds.
Oh, okay.
Will we ever need to like identify what kind of like structure is formed? Like, for example, like the alcohol versus ether. Like,
No.
would we
No.
ever need to be able to like figure
No.
that out? No?
Not at all.
No? Okay, thank you.
No. You will in my 306 class, though, but not in here.
Okay, thank you. That was my question. I guess that's why I was worried.
Oh yeah.
Is that like an organic chemistry question?
Yep, exactly.
Well, good luck, nurses.
The main focus of this is drawing your legal structures. And the more complex the formula, the more alternate legal structures you can have. So that's what I want to cover tonight, Lewis structures. And I'm going to put some alternate lab materials out. I thought I'd put them on there already, but I guess I didn't. And I'll have the answers as well. So everyone should get an 11 out of 11. But I don't want you doing these wrong and have to unlearn what you're doing wrong and relearn the right way. That's where I give you the answers. Now you're gonna have to draw some of these for the test on Tuesday. Already did any of you look at the practice test?
Yeah.
Yes, I did.
Now,
For this, professor, should we be memorizing the structure of these elements?
say again.
Just like, should we be memorizing like how carbon has 4 singletons?
Oh.
Should we memorize that?
Yeah,
And
you only have 5 of them. Yeah.
Okay.
The ones I circled here. Let me finish circling here.
And do we also have to memorize the rules, or will you give those to us?
I'll have those for you as well. But not
So wait,
all of
just to
Nothing.
double check what you just said. So the expectation is that we're supposed to memorize all of this?
the circled ones.
Oh boy.
Circled ones.
Okay. And you don't have to memorize the others because the periodic table will tell you what they are. So everything in the column is the same. So if you know oxygen, you know sulfur, selenium, etc. If you know nitrogen, you know phosphorus. If you know carbon, you know silicon, etc. That's why I had you only learn the top row. Because you're going to have a periodic table. I'm going to give you a periodic table on the test.
Can you go back to the top again where you had them circled just so I can finish making note of them? Thank you.
No, Professor, technically, I wouldn't even need to memorize them because if I look at the periodic table, I'll see that that one has 1, that one has 2, etc. Right?
That was my same thought process. Like if we know the periodic table, like you mentioned the val earlier in the class, then it would kind of
Yeah. So if you look at, and you have to be careful though. I mean, yes, but you have to be cautious in doing that. Okay, hydrogen is by itself 1 singleton. Boron is 3, carbon's 4 singletons. But see, nitrogen, once you get up to 5, they start pairing up. When you get to oxygen, they pair up again. When you get to fluorine, they pair up again. So yes, what you are just describing to me, yes, as long as you understand that pairing bit.
Right. And on how to draw the dots. Yeah.
Yeah, because if you have the 5 there on nitrogen, you'd have 5 singletons. There's not 5 singletons. There's only 3 because two of them are paired up. Oxygen should have 6 singletons, but it only has 2 because you have 4 of them are in 2 pairs.
Okay.
Yeah, those are really good questions. And if it practices a lot, you won't have to memorize them. You just, because you've used them so much, you'll know what they are. Easy for me to say. Okay, well, I'm fading fast here, you guys. I'm going to end this unless you have some more questions. Because I've got a few things I want to do tonight before I go to sleep. Oh, God. Sorry about that. I want to make sure you got the total Lab 7 parts. Number 1, and then number 2, I want to create the movie, the video.
Professor, do you think that there's a possibility you're still not going to be feeling well with that cough tomorrow, that we'd be doing Zoom again?
I feel guilty doing all these Zooms. I mean, theoretically, we could easily do it because we have dry labs tomorrow and Friday, tomorrow and Thursday. But I'd like to connect with you guys. So I'm gonna I maybe have a slight cough tomorrow because it seems to be getting a little better. I will see how it is tonight though. Whenever I lie down is when the phlegm builds up and it builds up. So so there's yes, there's a possibility. I'm gonna really push myself to be there though.
Don't push yourself. We'd rather you be healthy.
Well, I mean, I really feel the quality of your education is better if I'm there. So, okay. All right, let's see. Let me make sure I read all the chats. Destiny, I would suggest you do the ones that I posted in Canvas. They're easier than the ones that are in your lab packet. You can do either though and get credit for that.
Okay, and if we did the first packet, the last page, which has the acid and the AQ, we would skip that page as well, right?
Yeah.
Okay, got it. Thanks.
And then what we're gonna do is we're gonna do dry labs in lecture room. And then if you want to go upstairs to the lab, it'll be open. If you want to do them at home, you can do it at home. Dry labs are just really versatile. I like to be there for you when you have questions, though. So if you're kind of shaky on this stuff, do the dry lab in lecture. Okay, you guys. Thanks for all the nice things you guys say.
Hope you feel better. Hope you feel better, Professor. Thanks for getting online and trying to push yourself through it for us.
Well, I'm 76. I could have retired, 10 years ago, but I enjoy teaching a lot. That's why I keep teaching. So, all my friends, I should say almost all my friends, bug me, including my daughter. Dad, why don't you retire? Well, I did cut back though. I'm only teaching at Sac City from now on, not at Sierra as well. So my doctor suggested, he says, Ferguson, you need to slow down. You're getting old. Yeah. Okay, here we go. I'm going to stop sharing and stop recording.